Hello, hello. Can everyone hear me? Um, Hopefully, I can get you enthusiastic about working on Lightning. So my name's Connor. I work at Spiral. Spiral's an initiative at Block. We support open source Bitcoin developers through grants and through working on projects like the Lightning Development Kit. So I'm going to basically go through. So actually, show of hands, who's actually heard of the Lightning Dev Kit? All right, cool. So we've got a crowd that's quite familiar. So hopefully I can elucidate what it's all about to some of the newbies as well. So yeah, we've just heard a lot about Lightning from Ben. So the Lightning Network, yeah, scales Bitcoin by making it possible for anyone, anywhere to send fast and cheap payments. You know, at the heart of it, we have these payment channels that aim to kind of compress and condense transactions between peers, and Ben just showed us some maths that shows that we can only scale to a few orders of magnitude above what we currently have on chain. But let's talk a little bit about the actual developer experience with regards to building on Lightning. So my team, we spoke to a few years ago, a number of wallet developers before deciding to work on create experiences in mobile environments. Before LDK, if your team wanted to, integrate Lightning functionality into, let's say, a mobile application, you most likely had to modify one of the existing implementations and make it suitable for mobile devices or mobile constrained environments. Current implementations are good. They're like great out of the box node solutions, and they provide like these really good RPC and HTTP interfaces. But ultimately, they wallet into like a unified wallet experience, unified balance, or if you want to source Bitcoin blockchain data from a third-party server using like Explorer or Electrum, and you want to do this on resource-constrained devices, it can be quite complex and time-consuming, and maintaining tend to increase over time as your code bases age and the new use cases emerge with different performance and security kind of trade-offs. So yeah, standalone Lightning node daemons don't allow for much customizations ultimately, and developers with complex architectures don't necessarily have the ability to like modify those implementations. So yeah, let's talk a bit about what LDK is then. So LDK is a toolbox that provides developers a convenient way to build a Lightning node from scratch and create custom experiences. So it's in features that you want, but it's actually written as an SDK. So the core SDK is written in Rust, and we've created LDK to work in multiple languages with like this API first approach. And it's designed to ultimately run at the application layer. So this API approach means that developers are pretty much just required to call out APIs, and we have like a set of modules or components that developers basically have to plug into. So for example, we have something called the persist trait, or if you're more familiar with like Java, like an interface, which is responsible for determining how you back up channel state to disk before progressing through the Lightning state machine. And you don't need to run your own Lightning implementation from scratch. You can basically modify an existing one and plug into all of the LN functionality that already exists. So let's talk a bit about who's using LDK. The projects you see on the screen ultimately chose it for its and the ability to cater to different architectures without sacrificing security. So like I said, it has the ability to run in almost any environment. So you've got stuff like HSMs, hardware security modules, or embedded devices. This is something the VLS project is doing. So if you was at the workshop yesterday, you would have seen an example where you are able to ultimately run a Lightning node on an embedded device with very specific spending policies and be able to manage keys in a secure enclave, and then have some server stack with its own TCP, ICP connections, and basically pipe that through to your embedded hardware over like a serial cable, for example. And yeah, just to go through quickly some of the projects. So we just heard from Ben, Mutiny, one of the first self-custodial wallets to run directly in the user's browser. So they've written it because we don't have to rely on Google Play Store and the Apple Store and stuff like that. So it doesn't require users to download any software. And then we have Cash App, like very popular payments application in the US. They're using LDK as their Lightning implementation, primarily for its customization as well. And then we have stuff like Lexi, which I don't know, many people in here have heard of it, but it's in the cloud on a secure HSM or SGX. And this is great because it solves the offline receive problem, because you've got a node running in the cloud 24/7. Yeah, so just to elucidate a few more points on LDK. So we talked a bit about like its flexibility and customizability. So it is like truly like environment agnostic, many flexible modules, multi-language. So we support Rust, Kotlin, Java. So it's written in Rust. I think a lot of developers that I speak to, they tend to quite like Rust because you get an improved developer experience, but you still get kind of fine-grained control over memory and performance and things like that. So Rust is doing good things in the developer community at the moment. And yeah, it's versatile as well. Like we just saw on the previous slide, there are a number of different HSMs and LSP and routing nodes of that nature. So it really just depends on what you want to build. It's important to note here as well, so LDK is a public good. We're building a sustainable open source project that is welcoming to new contributors, beneficial to users, and it's not relying on any single funding source. The LDK maintainers spend like a significant amount of time reviewing code, answering questions, writing documentation, and we're always like welcoming to new contributors. So let's just do a very quick deep dive, or well, semi-deep dive into some of the architecture. Hopefully you can kind of see that. So this is just like a bird's eye view of how LDK works. So like I mentioned, it isn't a daemon, but it is an SDK that gets compiled down and run directly in your application. It is environment agnostic, so it knows pretty much nothing about things like your networking stack, the Bitcoin blockchain, data storage and persistence. All of these things are customizable by the application developer themselves, and you are able to provide these components depending on what architecture you're trying to go for. And on the kind of left side there, and this can be done, and we just wait in that minimum amount of P used, and that's so that enables like us within that transaction is ready to be. A bit about this as well. So one of the first, start building your own Lightning node, and this is handled in all the necessary gossip messages, and it also speaks to the peer-to-peer represented on this diagram, but we also have a in a nice need to implement that, provide the kind of raw and onto the next thing, and then we exchange channel required. And as a payer and as a recent updates to LDK's voice, LDK, we do this kind of HTLC forwardable method. So it's kind of interfaces, and then you handle a number of subsequent events that you call to do that. And they're successful when Quickly skim much of you'll be interacting with is like this is a method which requires you to so whether main sweep that you want to do, you can kind of determine that custom interface for broadcasting a set of Bitcoin transactions as well. And it does require quite a bit of Lightning knowledge for what to do, how to manage it. We create with a lot of sensible defaults. It's components that you so really. And this also supports that JavaScript, Flutter, React, and can tap into LDK nodes. Builders can work with commercial partners to self-host servers or go in. So providers, it can be quite a tool and come together. And there's a number of different projects working services, provide and just hook in and solutions kind of into. What's on the roadmap to go through when the receiver available in LDK now, so kind of have splicing, so the ability to resize Lightning channels, updates and scale updates as well. And then there is this kind of which will create their own just to swap in and out of LSPs to basically write time. If you want to app and Jeff on Twitter, Lightning Dev Kit, and to continue to work on Lightning. So, yeah.
Current use of Taproot in LEK and any.
Currently support Taproot channels, and yeah, per our roadmap for the fairs, there's a lot to build, and it will be coming down the line. Yeah.
Cool.
Cool. All right. Thanks, guys. Thank you.
Or 5, 6. Test. Cool. All right, hey y'all. Welcome to my talk. Definitions a little bit, as we go along. So if something is actually known explicitly within Bitcoin, how are clients actually call? We'll talk about Merkle tree validation. It's all about Merkle tree that is used in Taproot assets in order to validate, or even sort of like any state transitions within that. Then we'll talk about this, application to something. So first, what's a meta protocol? So, the thing is that Bitcoin is actually unaware of the protocol rules, right? For example, called maybe embed the data as maybe as far as like an op return, or maybe some like bit multi-sig outputs, or maybe others actually just embed a single hash in there. Dollar coins, under the umbrella of meta protocols, right? And on this list, most of them are actually variants actually sort of protocol is the questions like how do things actually work today. Like, so I think it's sort of like, two broad transaction in the blockchain itself, scale, right? So number one, this requires an entire full node. So basically, you have a protocol index itself, right? And if the protocol can be very, very large, right? The other thing is that it's also not very like client friendly, right? Because you basically require processing a terabyte of data with that. So it's actually sort of heavy because like if it's actually hard to verify clients have validation, I think some people would call this embedded consensus of the past. Well, and this is nice because now it's sort of like an explicit proof, right? Because you only need a like, which basically all the because of like clients, right? But now we'll talk about type-veracity. So what I mean by this is basically defined by the genesis block, and then you walk back Bitcoin itself. Those have different genesis blocks. So basically, therefore, those aren't actually something that's actually been followed all the proofs. Then you arrive at some split output on the other side, IDs, right? Because if you can't uniquely identify something, then it's unique because if you make software work that happened in the past, to basically ensure that all Coinbase addresses or outputs are actually unique, right? And this is also something that also avoid in the transaction actually creating this thing itself. Then you have the tag, which is the name, some metadata, the output index basically, and then also the asset type. And there's like collectibles or like normal assets itself, right? And that's how it is. So this is cool because globally unique asset IDs within the chain, which is a really cool property, right? And as you see layers, and these must have unique keys within itself. This is really cool because it's basically like client friendly, right? Like we actually have this commitment that's actually transaction, and the proof you can basically verify. So everything basically just looks normal, right? You can't necessarily like pick something out unless you have the just metadata, along with it itself and itself, right? And I mentioned a little bit earlier. So this thing has like a VM. Initially, it's basically just a TypeScript VM. In the future, we can actually swap the that's because now the top level balance is the sum. If you gave me some asset, basically, well, the output value should now be one less than what it was before. Maybe if you can do PSBTs, you can do normal swaps, you can do exclusion proofs, you can do a bunch of really cool stuff on top of it. Because the anatomy of how an asset lives in a transaction, right? First, you have like the TypeScript root, which has some additional leaves, and then there's like a special leave. Basically, you have the asset TLP, which has a witness, then also points to a previous asset, right? So that looks like obviously like I think the actual practical limit is like 2 to the 128 minus 1, I guess, if you have n actions basically. Either that's issuance or maybe that's transfer or other things as well too. And we have the Merkle Stern property, which means that succinct proofs, right? I want to prove the existence of the prior one itself. If you have something just simpler, like something that can actually never be split basically. So maybe it starts out manageable to a few kilobytes, maybe gigabytes. Once you get to the gigabytes and terabytes, at that point, then it's sort of like impractical. And maybe even at that point, like so basically you can have like change and split something more, right? But succinct proofs is a rescue, right? This is something that people talk about like a very long time ago. 10 years ago was considered movement back then, but I think now it's actually pretty practical. Now possible, and the field is still accelerating pretty quickly. Every few weeks or even a month, we basically have a student stew, something called RISC, which was featured in an earlier design architecture within these client-side protocols, right? Rest the proof that like the prior instance basically there. This also you can prove that like something else wasn't. The proof would actually also be doing things like patch or so, but it's still better than it being with the taproot assets itself. Another additional thing that basically takes the previous taproot and sort of like witness data and then gives you a new taproot thing. How it follows other rules, difficulty estimate, or whatever else. Or that's like has a leaf which has these attributes that have such and such properties with itself, right? Then you also have state transaction validity. You're saying, okay, well based on that instance inputs, which are actually maybe some in the block, you actually recurse. Then you say, okay, well, each of these inputs also has a valid inclusion. And then also now this is really cool because proof is basically a very cool property. Yeah, and then each basically validate something like this within Bitcoin script. What it actually looks like, and also maybe what are some of the benefits of doing so in the first place. First, we have like the initial first proof layer, the Merkle root within that itself, and then we know all the transactions. We can basically just use opt root it's going to be itself, right? So obviously we need to do additional 2 items, basically Merkle tree validation. We have that itself there. But one kind of a quirk with this is that like with the way Merkle trees work, like this script is actually dependent on the number of all of the values basically into the TypeScript tree, which can be kind of large. But maybe if you're operating off of fixed size Merkle trees, which is a little bit later, it can be a little bit easier, right? But then you basically unroll all these elements and then actually pick, within TypeScript, we actually use something slightly different. We basically use something called a Merkle sum sparse Merkle tree, right? And sparse Merkle tree is similar to Merkle trees. It's actually which is something called a tree people know about. And you can say, okay, well, obviously that's massive. That's like, a bunch of hashes. Like there's no way it's going to fit in RAM or anything like that. But the thing is, like, we can actually sort of like simulate this Merkle tree based off sort of like this empty hash construction, then continue on and so forth, right? So therefore, at every single level, we basically know what the empty hash already is. It's basically just a single hash, which is the top level empty hash value, right? So you can sort of like simulate this value to actually make it a lot more succinct, basically. And the interesting thing is, like, you actually don't need to unroll the validation applies the protocol a little bit because you can actually ensure you're always hashing the exact same amount of times. You don't need to unroll anything within it itself. And to the right, you basically see sort of like how we construct this empty hash map, basically. You basically have a map and then see exactly what level that thing is at, right? And then taproot assets basically goes another layer and basically adds a sum layer, right? So in addition to like, this, number hashing structure, that's actually the total sum of the supply basically, right? For example, we have something called a universal issuance tree where you're going to basically insert proofs of like the existence of all these assets, and then the top level value is going to be the sum of all the assets itself. So basically this makes it easier to do things like quote-unquote run numbers. Structure works where you're basically hashing these two, or you're summing the two values and then putting that into the digest itself, and you're based on like if you're branch or leaf. And one other thing, because it's like a trie, the way you do the lookup is that you're actually going to be looking at the individual bit on every single one of the keys, right? So each if it's a 1, you basically go right. And then you basically use this to basically go all down on the tree, and this is the thing because you can view it as sort of like every single element has a unique proof basically. So for example, with a Merkle tree, typically you need to like have all the leaves be sorted in order to inclusion proof. It's okay, well, it should be here, but it's not. For example, like if you're giving me something in this protocol, I want to add some additional new challenges as well. Because for example, like if we go back to the slide, you see we're actually needing to branch on the bit condition basically, right? Versus a Merkle tree where it's like sort of like descripted area disabled, and you need sort of like a routine that looks something like this. You can probably optimize a little bit further, all at once basically, and then split it up instead. And maybe you can do some simpler manipulations with that, or even just do it bitwise. If you just give me, then really nice. One other thing, you basically need arithmetic, right? You need basically if we're going to be having 32-bit elements within the value tree, maybe you also need 64-bit arithmetic or beyond basically in order to actually represent these things in an easy manner and larger operation within the tree itself, right? So now that we have all that, we can say, okay, well, how do we actually validate assets? So first, we can basically use opcat to construct the serialized TLV leaf, which is basically some more in the script key layer. Then you're going to actually hash that into basically the SMT root to derive this like top level script, which is actually then committed to within tap script tree. Then you're going to do another hashing layer beyond that to actually get the tweak that's actually going to be part of the taproot output, basically. But we do need a final layer. We basically need some sort of like opt tweak verify, basically effectively what something like opt check contract verify, opt CCV does itself. Because once you have that tweak, you need to be able to actually basically like something like opt EC add, EC mul, and opt internal key, basically to basically be able to verify the two components. But you need something like that itself, right? But then once you're able to verify the other tree, and that has this value, which is adds to this particular public key, I verify that something that actually exists as an asset within this itself, which is pretty cool. Conclusion is basically you have something in these series of trees, you follow all the rules. Now we actually need to follow state transition verification, right? For example, like uses Bitcoin script VM under the hood, which is really cool. So for example, we take sort of like this multi-input, multi-output structure. For example, like your asset is basically referencing a bunch of other inputs, which is sort of like a superset of a prevout. So in addition to basically the output, the TX hash and the index itself, you also then you need to give me the asset ID and the script key. So it's basically this for tuple to allow you basically uniquely navigate down this tree. And what we think from the BIP basically shows how you like map those inputs into one single output. So what we do, we actually insert all of the inputs into another tree, which is also an SMT, and that sum is going to be the sum of all the inputs. Those fees are actually paid on the upper layer itself. Once we have that, we basically make something called like a fake virtual, a prevout basically, which is just the TX ID of the virtual transaction that we created here. Split, so you basically put that in directly, but something that's normalized can actually be split. So we have something called a split commitment root, which is sort of like a commitment that includes the actual output, then also all the change output as well too. Now we can verify these two things within itself. And the cool thing, once again, is that we have something called a script key, which is actually just a taproot output public key, right? So therefore, using these tricks, you can actually verify that, like, in addition to state transition validation, because you can use some of the opcat tricks to basically reconstruct the sig hash, of the virtual transaction itself, and then validate the signature that's included against that thing itself. So as I mentioned as well, like these are actually taproot output public keys. So in theory, you can actually do script validation as well, but that's going to need some sort of like opt-eval, and it requires you to basically recurse another layer. So for now, at least in this concept, the motivating factor of this one's like something we call Pocket Universe itself, right? So it's basically sort of like a commit chain type structure where every single block you're basically committing to some new state itself, and that state is sort of like this tree. And something called no-cust, which people memory and leaf within this tree itself, because that's committed to at the top, you can verify sort of like that things are being done properly. For example, if no one left the tree, the sum and so forth, basically, right? The cool thing about this is that, like, because now we're able to validate the not really spend it unless it follows the rules of this protocol itself, right? So, for example, it's going to commit to all the leaves, all the participants itself, and one thing is like because we also have signature validation, they need to prove basically like any single modification to the tree as far as giving the internal nodes and also the new leaf that's been modified itself. They can't also just like remove funds from it, so it's actually moving into the chain every single time, right? For example, otherwise, let's say I had just this in this one layer itself, which is very cool. There's been channels, which people saw in my tweet a little bit earlier. We did for the first Type channel on mainnet. You get system itself by sort of spending your Bitcoin and then creating something that represents it in that system itself, and then putting it into this construct, maybe enjoy some of the scalability benefits of off-chain contract can also be done in this, because this thing basically is a UTX. So that's talk, and if you think this stuff is cool, work on taproot assets, Bitcoin, Lightning, ZK stuff, we're hiring. Thank you. There's a question over here. To a TapScript root, and that root itself is committing to basically all of the asset or user balances within that root itself, right? So therefore, like we're spending that with basically one output on chain, but we can potentially have many different leaves that have been modified within sort of like the delta, which maybe is going to be a signature of a leaf that chain larger. We also get the witnesses this guy there showed. Ooh, I got a lot of bullet points. 1 second. One more, basically. Well, this is sort of like more succinct validation, right? So assuming, once again, require them to basically validate all of the headers, basically validate all of the Merkle trees, things like that within the system. encrypt stuff there. So that's really cool in that like if we run into like sort of like sidestep this, we can just use benefits as well. And I think this is cool because like in theory like there's a sort of like version of the protocol. So other more hash-friendly functions, we can use a different vector commitment. Paradigms we can follow. And I think, in terms of like order operations, I think we'll be pursuing this one first to basically start to actually, create ZK proofs of these ASA proofs as well, because that lets us address the scalability benefits. But I think then it would be manner. Otherwise, because you can't validate all this other, more fancy sort of like, like someone doesn't follow the rules. Otherwise, I think we'll be getting into some of these ZK stuff very compilation target, right? And much of our code is written into Go, and there's something called time to Go that can actually format some of these systems. Basically, we can reuse all of our code to generate this. Yep. Yeah, so I gave another talk last year at the Starkware conference, basically, and I talked about sort of like that portion, that like, you mean like Lightning gossip, right? Yeah, exactly, right? So today, like, once again, like, everyone downloads all of the Lightning, proofs, basically. They do all the validation, they fetch the block, which can be actually take some time. I think that's also why people like LDK made like the rapid gossip sync, basically. But in theory, if someone could publish a single root, basically, of what was considered the gossip state, and then also that root as actually a proof, that verify the proof, and then download the graph and say, okay, this stuff is actually valid, right? And this is like a step up. It's another really cool application. And I think that's cool because, many of these things can be done today in terms of like, proving out some of the tooling without necessarily modifying Bitcoin as is. And I think like there's a new proof system basically, and it's okay. Well, which one are we going to choose? Things need to settle down somewhat. It's not really showing signs of settling down. I think people are going the. I think there's something called Bitcoin Wildlife Project or Bitcoin Wildlife Sanctuary. That's really cool. That I think people will be very excited about soon. That's actually doing that very thing. So, thanks.